In the previous lesson, we defined the electric potential V, derived the gradient relationship E equals negative nabla V, and established Maxwell's second static equation, the curl of E equals 0. Today we introduce two important topics. First, the electric dipole, a pair of equal and opposite charges that produces a distinctive field pattern. Second, we derive how much energy is stored in an electrostatic field and define the energy density. An electric dipole consists of two charges, plus q and minus q, separated by a small distance d. The dipole moment is defined as P equals Q times D, and it points from the negative charge to the positive charge. For a dipole centered at the origin with its axis along Z, the potential at a far point where R is much greater than D simplifies to V equals Q d cosine theta divided by 4 pi epsilon 0 R squared. We define the dipole moment vector P equals Q dA-Z so that V equals P dot A-R divided by 4 pi epsilon 0 R squared. The electric field is found by taking E equals negative nabla V in spherical coordinates. E-R equals 2p cosine theta divided by 4 pi epsilon 0 R cubed, and E-theta equals p sine theta divided by 4 pi epsilon 0 R cubed. Notice that the dipole field falls off as 1 over R cubed, faster than the 1 over R squared dependence of a point charge. This makes physical sense. From far away, the plus q and minus q fields nearly cancel. An electric flux line, also called a line of force, is a curve whose tangent at every point is in the direction of the electric field E. Faraday introduced these lines to visualize fields. An equipotential surface is a surface on which the potential V is constant everywhere. Since E equals negative nabla V and the gradient is perpendicular to constant value surfaces, flux lines are always perpendicular to equipotential surfaces. Moving a charge along an equipotential surface requires zero work because E dot dl equals 0 along the surface. For a point charge, equipotential surfaces are concentric spheres. For a dipole, the pattern is more complex. Positive potential above the midplane, negative below, with the 0-volt surface at the midplane itself. How much energy is stored when we assemble a collection of charges? Consider positioning 3 point charges one at a time. The first charge, Q1, costs 0 energy. There is no existing field. Bringing Q2 to its position requires work equal to Q2 times V21, where V21 is the potential at P2 due to Q1. Similarly, Q3 requires work Q3 times the sum V31 plus V32. Adding these up and using the symmetry argument of reversing the assembly order, we get WE equals 1/2 times the sum of QkVk from k equals 1 to n, where Vk is the total potential at the location of Qk due to all other charges. For continuous charge distributions, the summation becomes an integral. WE equals 1/2 integral of rho V times V dV for volume charge. Similar expressions hold for line and surface charges. Starting from WE equals 1/2 integral of rho dash V times V d dash V, we substitute rho dash V equals nabla dot D from Gauss's law and apply a vector identity. After using the divergence theorem and noting that the surface integral vanishes as the bounding surface goes to infinity, we arrive at WE equals 1/2 integral of D dot E d dash V. Since D equals epsilon 0 times E, this becomes WE equals 1/2 epsilon 0 integral of E squared d dash V. We define the electrostatic energy density, WE equals 1/2 D dot E, which equals 1/2 epsilon 0 E squared, which also equals d squared divided by 2 epsilon 0. Units are joules per cubic meter. The total energy is then the volume integral of WE over all space where the field exists. This is a powerful result. The energy is stored in the field itself, distributed throughout space, not just at the charge locations. Let us work example 4.15 from Sadiku. A sphere of radius r has uniform volume charge density ρ0. Find V everywhere and the energy stored inside. From Gauss's law, we already know E. Outside, r greater than or equal to r. E equals ρ0 r cubed divided by 3 epsilon 0 r squared in the AR direction. Inside, r less than or equal to r. E equals ρ0 r divided by 3 epsilon 0 in the AR direction. For the potential outside, V equals ρ0 r cubed divided by 3 epsilon 0 r. Inside, requiring continuity at r equals r, V equals ρ0 divided by 6 epsilon 0 times 3r squared minus r squared. For the stored energy inside the sphere, W equals 1/2 epsilon 0 integral of E squared dV. Substituting and integrating in spherical coordinates gives W equals 2 pi ρ0 squared r to the fifth divided by 45 epsilon 0. This result tells us exactly how much energy the field configuration stores within the charged region. Let us review today's key results. The electric dipole moment is P equals QD. Its field falls off as 1 over r cubed. Flux lines are always perpendicular to equipotential surfaces. The energy stored in a system of charges is WE equals 1/2 sum of QkVk. In terms of the field, WE equals 1/2 integral of d dot E dV. The energy density is WE equals 1/2 epsilon 0 E squared. In the next lesson, we will move to Chapter 5, Electric Fields in Material Space, Conductors, Dielectrics, and Boundary Conditions.